Hi, in this video I want to talk about appendo. Hopefully walking through how we wrote the relation appendo will help you write the relation lookupo, and you do need to complete the definition of lookupo before moving on to the final part of the assignment. And as we talked about in the earlier videos, appendo is a relational form of the function append, which takes two lists, x's and y's, and appends them. So for example, the list 1, 2 appended with the list containing just 3 is the list 1, 2, 3. With appendo, any combinations of the three arguments, x's, y's, and z's, which is sort of like the output of append, can be logic variables. So for example, we can make x's a logic variable and ask the question, which list, so that's our unknown, appended to the list 3, 4 will give us the list 1, 2, 3, 4. And there's only one answer, and the answer here is the list 1, 2. And by the way, we're just being really careful with using the length function here, since we can potentially get an infinite list of answers, especially when we get to part 3 of the assignment. So that's why we're taking the first 100 elements of the state and computing the length on just that subset so that we don't infinite loop. So now let's scroll up and pretend that we did not have an implementation of appendo, and we want to write one. And we're going to use the definition of append here as a guide. So what we want to do is think about what it means for x's appended with y's to be the same as z's. And just like in append, we're going to think recursively. So what does that mean? We're going to think about a base case, and we're going to think about a recursive case. So the base case here, just like in append, is going to be when x's is empty. And in this case, what would it mean for x's appended with y's to be the same as z's? Well, y's had better be the same as z's. And I'm just going to use mathematical notation here, so we're not talking about relations here, we're just writing down the idea. Now, in the recursive case, x's is not going to be empty. So x's is going to be some value, let's just call it a, cons with a list b. And if that's true, then z's should also have a as its first element. So this a and this a should be the same. The rest of z's could be different from the rest of x's because we might have elements of y's in here, and that's okay. We have two different variables here, b and c. And our y's can be whatever we want here. But we also need to have that appendo of b, which is the rest of the element of x's, with y's should be the same as z's. So that's exactly what we have here, really. Think of the output of this entire, of the body of append to be z's, because that's really what's happening here. So here we have x's broken down into its first and rest of the elements, which is what's happening here. And this is, this should be c. And this is really what's happening here. And breaking down the output, this is the output here, z's, to its first, breaking it apart into its first element, a, and the rest of its elements, c. So now we need to write all of this down as relations. So since appendo is a relation, we need to work exclusively with just the microcanon constructs that we created. So we're limited to equality, disjunctions, conjunctions, and creating fresh variables. So let's write down the base case first, since it's the simplest. So the base case is we need to have both x's empty, so x's should be the same as t-null, which is how we're representing the empty list. And we need to have y's the same as this. And since both of them have to be true, we're going to use a conjunction. In the recursive case, what we want are three things. So I'm going to use a conjunction because all three things have to be true. So first, x's should be the same as, well, we're going to break down x's into its first element and the rest of its element. And we're also doing the same thing for z's. I'm going to break that down into its first element, which is the same as the first element of x's, and the rest of its elements, which could be whatever we want, and the recursive part where the rest of x's appended with y's should be the same as the rest of z's. So we used a few new logic variables here, a, b, and c, which means that we need to call fresh to get those logic variables in here, and there we go. So now we just need to combine these two together. So the idea here is that we can be in either the base case or the recursive case, and only one of these has to be true for x's concatenated with y's, x's appended to y's to be the same as z's. So the operation we're looking for here is disjunction and not conjunction. And I think we have the same result as before. So if we hit run and run this one example, we should get the same answer. So the key insight from this video that I hope you'll take away is that you want to think recursively for a relation like lookup-o, and you need to only use microcanon constructs like conjunction, disjunction, fresh, and equality. The moment you start using this double equality or things like pattern matching, those are just going to make your relation not a relation and not work. So hopefully this video helps you figure out how to approach lookup-o.